Wireless communication forms the invisible backbone of our connected world, enabling everything from smartphone calls to smart home automation through sophisticated electromagnetic transmissions that most users take for granted. At its core, all wireless technology relies on the same fundamental principle: converting information into radio waves that propagate through the air before being decoded back into usable data by receiving devices. Wi-Fi networks operate primarily on two frequency bands, 2.4 GHz and 5 GHz, with the higher frequency offering faster data rates but shorter range, while cellular networks utilize a broader spectrum ranging from sub-1 GHz bands for wide area coverage to millimeter wave frequencies, 24 to 40 GHz, for ultra-high-speed 5G connections. When you connect your smartphone to a Wi-Fi router, the device first scans for available networks by detecting their beacon frames, regularly broadcast packets containing the network's service set identifier, SSID, and capability information. Upon selecting a network and providing the correct credentials, if secured, your device establishes a two-way digital conversation with the router using carefully choreographed transmission protocols that prevent data collisions on the shared wireless medium. The router, typically connected to a broadband modem, serves as the gateway between your local wireless network and the broader internet. It uses packet switching to route your data requests appropriately, while managing multiple simultaneous connections through techniques like time division and frequency division multiplexing. Wi-Fi employs carrier-sense multiple access with collision avoidance, or CSMA-CA, to regulate transmissions. Your device listens to ensure the channel is clear before transmitting, and if interference occurs, it waits a random back-off period before retrying. This process is managed automatically by the Wireless Network Interface Controller, or WNIC, in your device. Modern Wi-Fi 6, also known as 802.11ax standards, have introduced orthogonal frequency division multiple access, or OFDMA. This allows a single transmission to carry data for multiple devices simultaneously by dividing channels into smaller subcarriers. This dramatically improves efficiency in device-dense environments like apartment buildings or offices. Cellular networks operate on similar principles, but with far greater complexity to enable seamless mobility across wide geographic areas. Your smartphone constantly communicates with nearby cell towers even when idle, performing measurements of signal strength and quality to ensure it remains connected to the optimal tower as you move. These towers, formerly called base stations, are arranged in a honeycomb-like cellular pattern, giving the technology its name, and connected to the mobile carrier's core network through high-capacity fiber optic backhaul links. When you make a call or request data, your phone establishes a dedicated communication channel with the tower using specific frequency bands allocated to your carrier. Technologies like 4G LTE employ multiple input, multiple output, or MIMO antenna systems to improve signal quality by transmitting and receiving multiple data streams simultaneously. The cellular network handles your mobility through intricate handover processes. As you move toward the edge of one cell's coverage area, your phone and the network coordinate to transfer your connection to the adjacent cell tower with minimal interruption. This is a process that happens seamlessly during calls or data sessions in well-designed networks. Modern 5G networks have introduced network slicing, allowing carriers to create virtualized subnetworks optimized for specific use cases. These use cases include massive IoT device connectivity or ultra-reliable low-latency communications for autonomous vehicles. Both Wi-Fi and cellular systems employ sophisticated modulation schemes like QAM, quadrature amplitude modulation, to encode digital data onto radio waves. Higher-order versions, such as 256 QAM or 1024 QAM, pack more bits into each waveform cycle for faster throughput, albeit with greater susceptibility to interference. The security aspects of wireless communications involve multiple layers of protection that have evolved alongside the technology. Wi-Fi networks typically employ WPA3 encryption, also known as Wi-Fi Protected Access 3, as the current standard. This uses 256-bit cryptographic suites and individualized data encryption to protect each user's traffic, even on shared networks, addressing vulnerabilities present in the older WPA2 protocol. The encryption process begins during the four-way handshake when a device joins the network. Here, the router and client device authenticate each other and derive session keys used to scramble all subsequent communications. Cellular networks implement even more robust security measures, with LTE and 5G employing mutual authentication where both the device and network verify each other's identity using credentials stored on the SIM card. This is combined with strong encryption algorithms like 128-bit or 256-bit AES or Advanced Encryption Standard for over-the-air transmissions. However, wireless security remains an ongoing challenge as researchers continually discover vulnerabilities. From the crack attack that exploited weaknesses in WPA2's handshake process to IMSI catchers that can intercept 2G and 3G cellular communications, these issues drive continuous improvements in wireless security protocols. Emerging technologies like Wi-Fi 6E, which extends into the 6 GHz band, and 5G millimeter wave networks, introduce both new opportunities and security considerations. Their shorter wavelengths require different antenna designs and propagation characteristics that affect both coverage and potential interception risks. The physical layer of wireless communication reveals fascinating engineering solutions to real-world propagation challenges. Radio waves behave differently across frequency bands. Lower frequencies like 600 MHz or 700 MHz used by cellular networks can travel farther and penetrate buildings more effectively, but offer limited bandwidth, while higher frequencies like 5 GHz Wi-Fi or 28 GHz 5G mmWave provide greater capacity but are more easily blocked by walls or even rain. Antenna design plays a crucial role in optimizing wireless performance. Your smartphone contains multiple antennas for different frequency bands and technologies, Wi-Fi, Bluetooth, cellular, often using adaptive beamforming techniques that electronically steer signals toward the strongest path rather than radiating equally in all directions. Modern MIMO, or multiple input, multiple output, systems take this further by employing multiple antennas at both the transmitter and receiver. This approach creates parallel data streams that multiply throughput without requiring additional spectrum. The transition from 4G to 5G has introduced massive MIMO arrays. These arrays come with dozens or even hundreds of antenna elements at cell towers. This technology enables precise beam steering that tracks user devices as they move, while minimizing interference between connections. Wireless signals also contend with multipath propagation. This occurs when reflections off buildings, terrain, and other objects create multiple versions of the same signal arriving at slightly different times. Modern systems actually exploit this phenomenon to improve performance through advanced signal processing, rather than treating it as interference as early systems did. The network architecture behind wireless communications forms an intricate hierarchy that balances centralized control with distributed processing. In Wi-Fi networks, the access point or router handles medium access control and typically connects to a broadband gateway providing internet access. More sophisticated enterprise deployments use controller-based architectures that coordinate multiple access points for seamless roaming. Cellular networks employ a far more complex infrastructure. Your smartphone connects to a radio access network, or RAN, consisting of cell towers and small cells. This network backhauls traffic to a mobile core network, which handles authentication, billing, and interconnection with other networks. The core manages critical functions like mobility management, which tracks your location as you move, session management, which maintains your data connections, and subscriber data, which includes your account and services. Cloud computing has revolutionized this architecture through Network Function Virtualization, or NFV, where software running on commodity servers replaces specialized hardware, and software-defined networking, or SDN, which separates the control plane or decision-making from the user plane or data forwarding for greater flexibility. These innovations enable features like edge computing in 5G networks, where applications can process data closer to users by leveraging distributed servers at cell sites rather than relying solely on distant data centers, reducing latency for time-sensitive uses like augmented reality or industrial automation. Looking toward the future, wireless technology continues evolving to meet exploding demand for connectivity. Wi-Fi 7, also known as 802.11b, expected to be finalized in 2024, promises theoretical maximum speeds up to 46 gigabits per second through wider 320 MHz channels, higher 4096 QAM modulation, and multi-link operation that aggregates multiple frequency bands simultaneously.